When we think of energy, we imagine something in motion: wind turning turbines, water rushing through a dam, nuclear reactions splitting atoms apart. But there's another form of energy that is far stranger, far more subtle, and far more vast than all of these combined. It doesn't require fuel, it doesn't produce smoke or waste heat, and it doesn't even need matter to exist. It's everywhere in the space between stars and the air between atoms. It is zero-point energy, ZPE, the hidden engine of the universe. To understand it, we have to start with a fundamental truth of quantum physics. There is no such thing as complete stillness. Even at absolute zero, the coldest possible temperature, particles never truly stop moving. The reason is rooted in the Heisenberg uncertainty principle, which states that you cannot know both the exact position and the exact momentum of a particle at the same time. If a particle were perfectly still, we'd know both values exactly, which nature forbids. So instead, particles are forever jittering, vibrating and fluctuating in a restless quantum dance. That constant motion means they always have some energy, even in their lowest possible state. That is zero-point energy. The scale of it is staggering. Physicists calculate that the energy density of the vacuum, the empty space between particles, could be as high as 10 to the power of 110 joules per cubic meter. To put that into perspective, a single cubic centimetre of empty space could contain enough energy to boil all the oceans of Earth many times over. The fact that we don't see this energy bursting into our reality uncontrollably is a puzzle, and one of the great unsolved mysteries in physics. Some theories suggest that the vast majority of this energy is locked away, invisible to us because it's perfectly balanced in all directions. Others hint at hidden structures in the vacuum that might one day give us a way to access it in controlled amounts. We already have proof that the vacuum is not inert. The Casimir effect is one of the most famous demonstrations. Place two uncharged metal plates just a few nanometers apart in a vacuum, and they are pushed together by the pressure of virtual particles popping in and out of existence. This is not science fiction. It's been measured with extreme precision in laboratories. Another example is the Lamb shift, a tiny change in the energy levels of hydrogen atoms caused by the interaction between the electron and the zero-point fluctuations of the vacuum. These effects prove that the vacuum is an active, dynamic medium. The challenge is turning that into a practical energy source. Zero-point energy is, well, uniform and omnipresent, so there's no natural flow to tap into the way we do with wind or sunlight. To extract it, we'd have to create an asymmetry, a controlled imbalance, so that energy moves from one state to another in a way we can capture. This could involve tuning materials to resonate with specific frequencies of vacuum fluctuations, using nanoscale structures to enhance certain modes while cancelling others. Think of it like pushing a child on a swing. If you time the pushes just right, you can build up motion from a very small input. In the same way, if you can align with the natural resonances of the vacuum, you might coax energy into usable form. The potential applications are almost beyond imagination. In power generation, zero-point energy could give us compact, portable generators that run indefinitely without fuel. In transportation, spacecraft could use it to power engines that never need refueling, enabling interstellar travel without massive fuel tanks. In medicine, zero-point energy-powered devices could make advanced diagnostics and life support systems available anywhere, even in remote locations without infrastructure. And because the vacuum is everywhere, these devices would work in deep space as easily as they do on Earth. Some researchers are also exploring zero-point energy in the context of advanced propulsion. Concepts like the so-called quantum vacuum plasma thruster aim to generate thrust by interacting with the zero-point field directly, without expelling reaction mass. If viable, such a system would, well, revolutionize spaceflight, eliminating the rocket equation's limitations and making long-duration missions far more practical. While these ideas are controversial and unproven, they are based on the same quantum principles that give us the Casimir effect and the Lamb shift, real, measurable phenomena. One of the most compelling aspects of zero-point energy research is how it forces us to confront the deep connection between energy, space, and time. Einstein's general relativity tells us that mass and energy curve space-time, and quantum field theory tells us that space-time itself is filled with fluctuating energy. This hints that zero-point energy may play a role in the fabric of reality itself, possibly linked to dark energy, the mysterious force driving the accelerated expansion of the universe. If that's true, then understanding zero-point energy isn't just about building better batteries. It's about understanding why the universe behaves the way it does. Of course, with potential this vast, there are risks. Any technology capable of tapping a universal energy source must be developed with extraordinary care. Zero-point energy is not a magic box. It's a deep, physical phenomenon, and any attempt to manipulate it on a large scale could have consequences we can't yet predict. This is why rigorous science, transparency, and international cooperation will be essential if and when we begin to move from laboratory experiments to real-world systems. The bottom line is this: zero-point energy is real, measurable, and unimaginably abundant. The challenge isn't proving it exists, it's finding the key to unlock it safely and sustainably. We're still in the early days, but the groundwork is being laid in labs around the world. If we succeed, the world will never be the same. Imagine a civilization where every home, every vehicle, every device draws power directly from the quantum fabric of space. That's the promise of zero-point energy, and it's a journey worth taking.